It's Carly McAvoy. We're going to look at Chapter 4B today, and I think I'm going to get halfway through this. I have to leave in about 35 minutes. I don't think I can do the whole thing, but we're going to get through what we can. So the first question, I'm going to flip over to my handwritten stuff, but talks about a procedure called acceptance sampling, which is sampling. You have a big batch of things and you sample 3 or 4 of them, and if you have 3 or 4 of them and they all come out to be acceptable, then you accept the whole batch. So there's some risk in that, right? So we always wonder, what's the probability that if you have some, there's some defective ones in there, let's say there's 100 defective ones in there out of 2,000, and you select 5 of them, what's the chances that you're going to get all good ones? So you know that you're going to be sending out some defective product, and that's cheaper to replace and have angry customers is better than having to look at every single product and make sure it's not defective. That's that. So when you buy things that cost more, a lot of times you have a better guarantee because I spent some more time on that. Okay, so we're going to flip over to my paper, and I'm going to show you how to do this. It's not complicated, but what this says is that this method, there's 1,864 CDs. They have this acceptance sampling policy, has manufactured 1,864 CDs, and 838 are defective. So I want to subtract the ones that are defective and figure out the ones that are not defective, or the number of the ones that are not defective. And I think I'll put my calculator away, so I need it because I don't want to do that by hand. That subtraction is so woefully hard. So anyway, 1864 minus 838 defective, which gives me 1,026 that are not defective. Okay, so the question is, if 3 of these CDs are randomly selected for testing, what's the probability the entire batch will be accepted? So we're looking at the not defective because they want to pick 3 and they're all going to be good, and so they accept the whole batch. So we're going to take 1,026, that's the probability of selecting one that's not defective, and we're going to divide that by the probability of all of them, the whole sample space. And we want to do that 3 times. So we want to draw 3, and we want all 3 of them to be not defective. And so essentially when you put that into your calculator, what I would do, if you have the great calculator that I have, is I would put the 1,026 and dividing by 1864, and then I would just take that to the 3rd power because you're multiplying that 3 times. So that to the 3rd power because you're selecting 3. If you were selecting 5, you take it to the 5th power, and if you were selecting 12, you take it to the 12th power, right? Anyway, that's the number of ones you're selecting. And so that gives me 0.166. What do they ask for here? They asked just for 3 decimals, 167. All right. Don't look at that. Does the result suggest that an entire batch consists of good CDs? So you have this. This means there's a 17% chance if we pick 3 that we would get all. They're all good, and that we're going to select 3 that are good. No, it doesn't suggest that we have all good. What if I had a probability of 1? That would be the only way to say for sure, 100% positive that I'm going to get all 3 of those to be good. If I had that, if it was 100%, then I'd know I had an entire batch of good ones. But if I have any percent at all down here that's not 1, then it's like, yeah, there's definitely a chance that I'm going to select a bad one in the process of picking out 3. And if I picked out, let's say, 4 or 5, there's even more of a chance, right? So acceptance sampling comes with a risk. Okay. The principle of redundancy is used when system reliability improves through redundant or backup components. Assume that a student's alarm clock has an 8.4% daily failure rate. Get rid of the alarm clock, but for our purposes, whatever. But there's a chance, 8.4% chance that it does not go off. What is the probability that the student's alarm clock will not work on the morning of an important exam? Well, we just were told. To 3 decimal places. What do they want 0.04? Okay. If you move that over 2 places, we get 0.084. That's the probability that on a morning of a test it's not going to work, because it tells us every single day there's that. If a student has 2 such alarm clocks, what's the probability they both fail in the morning? So if you had 2, you have a 0.084 probability of failure, but you've got 2 of those. So if you multiply those together, or 0.084 to the second power, whoops, then you have a 0.007 chance. Okay, so now here we had an 8.4% chance. By putting 2 clocks in that are just independent clocks, we go down to a 0.007, or 0.7% that that's going to happen. What if the student got 3 clocks and had set 3 clocks up? Then they're going to take this to the third power, and 0.084 to the third power is 0.00059. Oh, look, they told us to round to 5 decimal places here. How random is that? I can't stand that. But anyways, okay, so that's 0.06 out 5 places, and then that's 0.0059. 0.059. Do the second alarm clock result in greater improved reliability? Well, you know, you had an 8.4% chance of malfunction when you had 1 clock, and you're down to this probability of having a malfunction with 3 clocks. So yeah, it definitely would be unlikely to have all 3 of your clocks fail if you had all 3 of them lined up to go. Okay. Assume that a company hires employees on Monday, Tuesday, Wednesdays, or Thursdays, 4 different days of the week with equal likelihood. If 2 different employees are randomly selected, what is the probability they were both hired on a Tuesday? Well, what's the probability that one person is hired on a Tuesday? 1, 2, 3, 4 days. First person, there's a 1/4 chance that they get hired on a Tuesday. So then the next person comes along. This is an independent event. When the first person got hired doesn't affect the second one. So the second person has also got 1 out of 4 chance of being on a Tuesday. So therefore we have, whoops, that's not what we have. We have 4 times 4, or 1/16 of a chance. Sorry, that's 1/16 of a chance. They want a simplified fraction there. 1/16 of a chance to get hired on the same day, on the same Tuesday. If 2 different employees are randomly selected, what's the probability they were both hired on the same day of the week? Well, that could be the case for any day, right? We don't know if they're talking about Mondays, Tuesdays, Wednesdays, or Thursdays. But I do know that when somebody came in and got hired, there's a 100% chance they got hired on Sunday. So let's give that a 1, because 100%, yeah, they did get hired. And then whatever day that is, because there's 4 days, the second person has 1/4 of a chance of getting hired on that same day. 1 times 1/4 is 1/4 for that. What is the probability that 6 people in the same department will be hired on the same day of the week? And is that event unlikely? Before we even figure out the numbers, we should be able to say, sounds unlikely that they're all going to be happening on the same day if it's all just randomly occurring. But just like part B, the first person gets hired on Sunday, and then the next 5 people have a 1 in 4 chance of being hired on that same day. 1, 2, 3, 4, 5, like that. And then we're going to take 4 to the 5th power, which is 1024. So I have 1 over 1024, just multiplying across here. So this is unlikely, because the probability 1 divided by 1024 is 0.00098, let's say, chance. And that's less than 0.05, which means that it's really unlikely. That is it unlikely? The answer is going to be yes, and you can read which one of those you think fits that scenario. All right. Number 4. The data below table summarizes results from 115 pedestrian deaths that were caused by accidents. If 2 different deaths are randomly selected without replacement, find the probability that they both involved intoxicated drivers. And is such an event unlikely? Well, with 115 possible, we do not replace, which means I have 115 people in my first set, but then my second person that I select is only going to have 114. You see what that means by not replacing? We're not putting that person back in the pool. Okay. If two different deaths are randomly selected without replacement, okay, without replacement makes this happen. Find the probability that they both involved intoxicated drivers. Okay, where's the intoxicated driver? Driver intoxicated, yes. All the way across here, driver intoxicated was 48. Right? There's 48 people, drivers that were intoxicated. So the first time I draw somebody out of there, that's 48, because I had 48 people out of 115. And the second one is 47, because I didn't replace that intoxicated driver back in my study. So 48 times 47 is 2256, and then 115 times 114 is 13110. 2256 divided by 13110 is approximately, and it says to go to 3 places, 0.172. Is that unlikely? I did some rounding there. It'd be better if you did this in your calculator like this. This fraction, 48 over 115 times 47 over 114. I get the same thing again. Well, driver intoxicated, yes. Looks like 48 to me, and then intoxicated drivers. I don't know. I got 0.172. They got 0.174. So I'm going to just move on from there. Okay, but is it unlikely? This is not unlikely. Unlikely if it's less than 5%, right? So it's not unlikely because its probability is greater than 5%. All right. A tire company produced a batch of 6,200 tires that includes only 270 that are defective. If 4 tires are randomly selected for installation in a car, what is the probability that they are all good? So we have 6,200 total, and we have 270 that are defective. So if we take off the 270 that are defective, we have 5,930 that are good. We're going to take 4 of those, so we're going to take 5,930 divide by 6,200 and take that whole thing to the 4th power, because we're selecting 4, just 4 good ones, and that's the chance of a good one out of our total batch. Okay, so we have this fraction, 5,930 out of 6,200, and then we want to take that because we got 4 tires, and we have a 0.8. What do they want us to round to? 3 places. 0.837 approximate chance to get that right. 4 tires that are all good. If 100 tires are randomly selected for shipment, what is the probability that they are all good? Well, now we have this same chance, 5,930 out of 6,200, but instead of 4 of those, we have 100 of those, right? So we have 5,930 over 6,200, and we have raising that to the 100 power. The chance that all 100 of them are going to be good, way, way, way less, right? To 3 decimal places is 0.012. Oh, we have a 1.2% chance that 100 of them are actually going to be good. So there's probably going to be a bad one in there, right? 99% of the time we're going to get at least a bad one. Should this outlet plan to deal with defective tires? Well, if you have 100 tires and you only have a 1% chance that they're all good, then you're going to have some bad tires, right? And that means yes, because there's a very, very small chance that all tires are good. So we want to say B. There's a good chance they're going to have to deal with that as they go through their process, even with a pretty small number of defective ones. Okay. All right. Let event A, the subject is telling the truth, and event B, the polygraph tests indicate that the subject is lying. Use your own words to translate the notation this. B given A, right? Conditional. this says that the B event is the polygraph test indicates. So that's the first one that's got to be stated because it's on top. The polygraph test indicates that the subject is lying. The polygraph indicates lying. The polygraph indicates lying. So it's B or D. I have no idea why none of these ever print off. It just sort of bugs me. But anyway, we know that they're lying because that's the B event. The polygraph indicates that the subject is lying, given that the person is actually telling the truth. Given that they are actually telling the truth, because A is telling the truth. So this says, the polygraph says that you're lying when you're actually telling the truth. That's bad mojo, right? Okay. Describe the written description of the complement of the given event. When 15 cameras are shipped, at least one of them is free of defects. So when you say at least one of them is free of defects, that means that they're not all bad. There's at least one that's good, right? At least one of them. So you have 20 kids, at least one of them is going to graduate high school or whatever. That means that you think that not all 20 are going to fail. So the complement of that is that none of them are defective. No, I'm saying all of them are defective. This is saying this at least one of them is free of defects means that not all are defective. That's what that really says. There's not all of them are. Somebody's good in there. Something's good in there. So the complement that is the opposite, which is that all of them are defective. I think these are tricky. I just got it wrong myself, but I kind of skipped some. I should have written that down. This, at least one of them is free of defects, means that there's one of them that's not defective. So not all of them are defective. So the complement is they are all defective. Okay. All right. When 12 digital pianos are received, none of them are defective. If you say none of them are defective, that's just about the opposite of what here, right? None of them, well, it's not the opposite, but think about that. None of them are defective. If none of them are defective, then the complement of that would be just at least one of them is. Because that would ruin your day, right? You said none of these are defective, and then we've showed that one of them is defective, then we've negated your statement or shown the complement of it. So for none of them, the negation or the complement of that is at least one of them. It's not very intuitive, but that's how that goes. Okay, if a couple plans to have 5 children, remember what I told you in an earlier video about if there's children are considered to be 50% chance boy-girl. And so when you have 2 different outcomes, the total sample space is always 2, which is the number of outcomes, to whatever power, which is however many you're going to have, how many times you're going to roll the dice or flip the coin or have children. So 2 to the 5th means there's 32 outcomes here. 32 ways you can have it. A boy followed by all girls, a boy followed by 3 girls, that kind of thing. What is the probability there will be at least one boy? At least one boy means there could be one boy, there could be 2 boys, could be 3, could be 4, could be 5. The only thing that's not true is that there's 0 boys. There's no way you're going to get 0 boys. So the only way when you list all those out, there's one way. Because if it's all girls, then you didn't get any boys. But if you have at least one, means every other thing. So that means out of the 32 probability, there's only one that doesn't work out. And one is the when you have all girls. So if you have 5 girls and no boys, that happens 1 out of 32 times. So the probability of getting at least one boy is all the other ones, which is 31 out of 32 times. All right? And so that's an integer. They want a fraction, yeah. Can the couple be confident that they will have at least one boy? Yes, they should be pretty confident because the probability is so close to 1. I mentioned in an earlier video 5 to 6 kids in my family. My parents' first child was a boy, and they wanted another boy. So they had 5 girls in a row and did not get another boy. So it's possible that even though it only happens 1 out of 32 times, you could have 5 girls in a row. But it's not very likely, right? So they had a good chance, but they missed it. They should have played the lottery on that one. Okay. Find the probability of a couple having a baby boy when their sixth child is born, given that the first 5 children were all boys. So you had 5 boys and you're hoping for a 6th child to be a girl. What's the probability? Well, the truth is, no matter what you had before or after, it's shown that it's still a 50-50 chance. So no matter what you had before, the probability is still 0.5. It's the same whether you had just had your first one or your second one or your 12th one. It's still 50-50 for each kid. Are the results the same as getting all boys? Is this the result the same as the probability of getting all boys among 6 children? That is not the same, because when you have 6 kids, you have 2 to the 6th or 64 different outcomes of that, and that's not the same as this. This is just saying for 1 kid there's a 50% chance, but obviously for 6 kids you have 64 different outcomes, so that's not the same. The second way involves a lot more possible outcomes. Okay, all right, based on